Hello guys, we're going to do 8.3 today, which will be very, very similar to 8.2, which was all about arithmetic sequences. Now we're going to switch and look at geometric sequences. So for objectives today, we're going to recognize, write, and find the nth term of geometric series, or sequences, excuse me. Then we're going to find the nth partial sum of geometric sequences. Then we're going to find the sum of infinite geometric sequences, right? So how do we add a series that goes on forever? And then lastly, we're going to use our geometric sequences to solve real-life problems. Okay, so geometric sequence is just a sequence that's multiplying by the same number every single time. So arithmetic, right, was adding and subtracting by the same number every single time. Geometric is multiplying by the same number every time. The number that we're multiplying by every single time is the common ratio, and that is found by this little formula right here. Really, this is what I use, actually, if I can't tell just by looking at it, a lot of the times you can tell just by looking at it. But if you can't tell just by looking at it, you can just do the second term divided by the first term. And that'll tell you what your R is, your common ratio. That's what you're multiplying by every time. Here's the explicit formula for our geometric sequences. So it's your first term times your ratio to the n minus 1. So anytime you have that n in the exponent, you're likely looking at a geometric sequence. So let's look at example 1 here, just determining whether or not something is geometric and writing the first five terms. Okay, so looking at A, if I want to write the first 5 terms, I'm plugging 1. 2 to the 1 is 2. 2 to the 2 is 4. 2 to the 3 is 8. 2 to the 4th is 16. And 2 to the 5th is 25. So I'm multiplying. I don't know why I wrote 25. That is not right. It's 32. Wow. It's the end of the day. I'm tired. Okay, so R, in this case, we are multiplying by 2 every single time. So my R is 2. Therefore, this is geometric. You also could have found R by dividing for the second term, right, by the first term. So 4 divided by 2 is 2. Okay, so for B, if I plug in 1, 1 to the third is 1. 2 to the third is 8. 3 to the third is 27. 4 to the third is 64. And 5 to the third is 125. So a couple things. One, the n is not up in the exponent. Here I'm not multiplying by the same number every single time. So this is not geometric. Okay, for C, this looks like the geometric explicit equation, right? So let's find our terms. If I plug in 1, 3 to the 1 is 3, times 4 is 12. If I plug in 2, 3 squared is 9, times 4 is 36. And if I notice, right, this right here tells me what my R is. I'm multiplying by 3 every single time. So 12 times 3 is 36. 36 times 3 is 108. 108 times 3 is 324. And 324 times 3 is going to be 972. So here my R is 3, right? I'm multiplying by 3 every single time. So this sequence is geometric. Okay, and then the last one, if I plug in 1, negative 1/3 to the 1 is negative 1/3. If I plug in 2, negative 1/3 squared, I square the top, so negative 1 squared is positive 1, and 3 squared is 9. So I square the top and the bottom. I also can tell just by looking at it that my R is negative 1/3, meaning I'm multiplying by 1/3 every time. So negative 1/3. So if I multiply 1/9 times negative 1/3, I get negative 1 over 27. And again, by negative 1/3, I get positive 1 over 81. And by negative 1/3 again, I get negative 1 over 243. So this is geometric. So hopefully just recognizing it is not so bad here. Now let's find a specific term. So here the example says, finding the terms. Write the first 5 terms of the geometric sequence whose first term is 1. So my first term is 1, and my common ratio is 2. So all that means is, hey, my first term is 3. I said first term is 1, didn't I? Sorry. My first term is 3, and I'm just multiplying by 2 every time. So my second term is going to be 3 times 2, which is 6. And my third term is going to be 6 times 2, which is 12. So then my fourth term is going to be 12 times 2, 24. And then my fifth term is 24 times 2, which is 48. And that's it. It just wants me to write the first 5 terms. So go ahead and try this one. And then when you're ready to check your work, just hit play. Okay, so check your work here. My first term was given to me at 3, and then my ratio is 3, so I'm multiplying by 3 every single time. And so that's how I got my first 5 terms. So hopefully nothing too crazy there. Now let's look at finding a term, like a specific term, if I'm given some information. So example 3 says, find the 15th term whose first term is 20. So my first term is 20, and my common ratio is 1.05. And I want to find the 15th term. So I need to write the equation, right? So my equation was on the previous page, but it's a sub n equals my first term, which is 20, times my multiplier, my common ratio, which is 1.05, to the n minus 1. And so that is the explicit formula for my geometric sequences. Now I can find any term, but specifically I want to find the 15th term. So I'm going to plug in 15. And I have 20 times 1.05 to the 15 minus 1, which is 14. And this is something I can just enter into my calculator. Now, whenever we're doing these, you always want to check to see if you can turn your answer back into a fraction. In this case, you cannot. So it should just be 39.59. Let's just say 0.56. That seems easier. 0.56. And so that is the 15th term I should read. Okay. So this is what I mean by checking to see if you can put it into your calculator. So I'm going to do 20 times my 1.05 to the 14th. And that's how I get the 39.59. Now I'm going to go math, first option's fraction, and hit enter. Since it goes back to this decimal, that means that you can't write this as a fraction. So this is as close as we're going to get. However, if you can write it as a fraction, you should, because it's more exact, right? Decimals are an approximation versus a fraction is exact. So I want you to try this one. Find the 9th term, whose first term is 4 and whose common ratio is 1/2. And then when you're ready to go over it, hit play. So I know that my first term is 4, and I know that I'm multiplying by 1/2 every time. So I can write the equation. A sub n equals my first term times my common ratio to the n minus 1. Now I want to find the 9th term. So I'm going to have a sub 9 equals 4 times 1/2 to the 8th. And I enter this into my calculator, and it does convert back into a fraction. So we need to make sure that we do that. And I get that the 9th term is 1/64. And there it is. And that's it. Example 4 is adding on one tiny little step from that. It says find a formula for the nth term of the following geometric sequence. Well, in order to know the nth formula for the nth term, I need to know my first term, which I can look at it and see it's 5. And I need to know my r, which again, I can look at this and see that it's multiplying by 3. However, if you're ever looking at it and you're like, I don't know what it's multiplying by, just make sure that you do your A2 over A1. And that'll tell you what you're multiplying by. So I can write the equation, a sub n equals my first term, which is 5, times my common ratio, which is 3, to the n minus 1. So there's the first part that it wanted me to find. Then it says, what is the 9th term? So a sub 9 is going to be equal to 5 times 3 to the 8th. So my 9th term here is 32,805. So if I keep multiplying by 3, 9 times, I'm going to get 32,805. Okay, so try this one, hit pause, and then when you're ready to go over it, let's do that. Okay, so things I need to know. I need to know that the first term is 6. I also need to know my common ratio. Well, I don't know what I'm multiplying by here. So I'm going to take my second term, and I'm going to divide it by my first term. So actually, I'm probably going to write that out just so for notes we have it. So I'm going to take my second term, I'm going to divide it by the first term. So that gets me negative 2 over 6, which reduces to negative 1/3. So now I know that my common ratio is negative 1/3. So I can write the equation, right? My first term times my common ratio to the n minus 1. So there's the formula to find the nth term. Now the second part wants me to find the 10th term. So the 10th term is equal to 6 times negative 1/3 to the 9th. And again, if I enter this into my calculator, I am able to turn it back into a fraction. So it's going to be negative 2 over 65/61. And there we go. So the only step we added on there is we had to figure out what r was. Let's keep going with that theme. So example 5, we do still have to figure out what r is. But it's a little bit more difficult. It's going to be very similar to what we did with arithmetic sequences. Okay, so I'm given that the fourth term is 125. So I'm given the fourth term is 125. And I'm given that the 10th term is 125 divided by 64. And I want to find the 14th term. I need to know what r is. So I'm going to do what we did for arithmetic sequences. I'm going to say, hey, the 10th term is just equal to the fourth term, right? It's the fourth term times r, times r, times r, times r, times r, right, until I get to 10. So it's the fourth term times r, and then the difference there is 6. So r to the 6th. So I'm going to just plug this into my calculator. So 125 over 64 equals 125 times r to the 6th. And I can just enter this into my calculator. So I'm going to do 125 divided by 64. I'm doing that in parentheses so that my calculator knows that that is one fraction. And then I'm dividing that by 125. Again, I get a decimal. I don't want a decimal, so I'm going to convert it back to a fraction. And I get 1 over 64 equals r to the 6th. Okay, now I need to take the 6th root of this, right, so that I can find what r equals. So I can go into math, and number 5 here has the x above it. That'll allow me to enter 6, and then I can just do answer, and I get 1/2. The other way that you can do it, if you have one of the older calculators, you'll just have to hit the 6 first, then go to math and number 5, and then it'll put it up there for you, and then you can do 1 divided by 64.5, or 1/2. So my R is 1/2. So I know that I'm multiplying by 1/2 every single time. Well, that's great, but what I really want to know is the 14th term. So I can say, well, I know that the 14th term is going to be equal to the 10th term times R to the 4th. I know what the 10th term is. It's 125 over 64. And I know that R is 1/2. So I can enter this into my calculator. So again, I'm going to do 125 divided by 64 in its own parentheses times, I'm just going to say 0.5 to the 4th. You can do 1/2 too, but again, I get some crazy decimal, so I'm going to see, can I turn that to a fraction? And I can. So it's going to be, the 14th term is going to be 125 over 1024. And there it is. So I know that the fractions are pretty gnarly in this one, but you can do most of it on your calculator. Try this one, use the same idea, right? You're given that the second term is negative 18, and you're given that the fifth term is 2/3. So use the same idea, find what R is, and then find the sixth term. Okay, so hopefully you gave this a shot. So we know that the fifth term is going to be equal to the second term times R to the third. Okay, and I can plug these in. So 2/3 is equal to negative 18 times R to the third. Well, if I do that on my calculator, right, 2/3, it's its own fraction, I'm putting it in parentheses, divided by negative 18. Turn it into a fraction, I get negative 1 over 27. So negative 1 over 27 equals R to the third. And then I need to take the cube root of that. And we go math. And actually, cube root is already on there. It's number 4 of my answer. And I get negative 1/3. So negative 1/3 equals R. Once I know what R equals, now I can find the sixth term. So I can say, hey, the sixth term is equal to the fifth term times R to the 1. The fifth term is 2/3 times R is negative 1/3. So when I multiply straight across, I get negative 2 over 9, which is not able to reduce. So that's just my answer. All right, if you have any questions along the way, make sure that you're reaching out either as you're doing the notes or after the notes, whatever. We are going to kind of switch gears now and look at partial sums. So how do we find the partial sum of a geometric sequence? It's just an equation that we use. And again, you don't have to memorize these equations, but it is just an equation that we're given. So here it is. Same thing, you're going to have S sub n. So however many terms you're adding up is your n. Then you have your first term, your R, which is whatever your common ratio is. And then n, again, is the number of terms you're adding up. So let's look here. I need to know my first term, and I need to know my R. Well, my R is easy to see. It's right there in the parentheses. And my first term is if I plug in 1, right? So see right here, n is 1. That is my first term. If this was 7, my first term would be plugging in 7. This was 5, my first term would be plugging in 5. But this is 1, so my first term is plugging in 1. So 0.3 to the 1 is 0.3, times 4 is 1.2. Once I have that info, I can just say, hey, the sum of the first 12 numbers is equal to the first term, which is 1.2, times 1 minus 0.3 to the 12th, all over 1 minus 0.3. And it's just something that we can straight enter into our calculators. So let me show you the way that I do it. I personally do just the top first. So I do 1.2 times 1 minus 0.3. Now, only the 0.3 is being raised to the 12th, so you just need to make sure that you do that very carefully. Then I hit enter. Then I divide it by 1 minus 0.3. Again, in parentheses. And I get 1.714. So the sum of the first 12 numbers is 1.714-ish. Okay, try it over here, right? Find your first term, find your R, and then find the sum of the first 7 numbers. All right, so let's look at this. My first term, if I plug in 1 minus 1 is 0, and 2 to the 0 is 1. So my first term is 1. And my R is 2, because that's what the base of my exponent. So let's find the sum of the first 7 terms. So it's going to be my first term, which is 1, times 1 minus 2 to the 7th, all over 1 minus 2. And we should have gotten that our 7th term is 127. If you're having trouble entering that into your calculator, just reach out and let me know. I'm sure it's just missing parentheses or something like that. Okay, now let's look at infinite sums, or infinite series, excuse me. How do I add up a sequence that goes on forever, right? I can do it as long as the absolute value of R is less than 1. So 1/3, 3/4, 2/5, whatever, right? I can use this formula where it's just the first term over 1 minus my common ratio. If my R is greater than or equal to 1, I cannot add them up. The infinite series does not have a sum. We say that it diverges. If the sum does exist, we say it converges. Okay, so I'm going to scroll down here a little bit more. There we go. So let's look at this. We're not going to use our graphing calculator. We're just going to find the first 6 partial sums. So again, things I need to know. I need to know my first term. Well, if I plug in 1 minus 1 is 0. 0.6 to the 0 is 1, and 1 times 4 is 4. So my first term is 4, and my R is 0.6. And I want to find the first 6 partial sums. So the sum of the first 6 is going to be my first term times 1 minus my ratio to the 6th power, all over 1 minus 6. And I do some calculator work, and I get that the sum of the first 6 terms is like 9.53344. And I'm purposely writing out a ton of numbers there just because I want to show you something. So there's the sum of the first 6 terms. Now I want to find the sum of the infinite series, right? Do you see how it's going on to infinity? And I can do that because 0.6 is less than 1. So we just use an S. There's no subscript. We're using this formula right here. Okay, so it's equal to the first term, which is 4, over 1 minus my R, which is 0.6. This leaves me 4 over 0.4. So the sum of this infinite series is 10, meaning that every time I add on a new number, it gets closer and closer and closer. The sum, right, gets closer and closer and closer to 10. And I keep going on to infinity, and it keeps getting infinitely closer and closer and closer to 10. So the sum of the first 6 terms is 9.5, whatever. Maybe the sum of the first 100 terms is 9.7. And then the sum of the first billion terms is 9.85. And then the sum of the first trillion terms is 9.91 or whatever, totally making up those numbers. But the point is that as I keep adding numbers, I will get closer and closer and closer to 10. And so that is the sum of the infinite amount of numbers. I'm cautious to say this because this is not like an asymptote, right? It's not an asymptote. Like there's no graphing, there's no like points going towards an asymptote, but it's similar to it in the idea that as I go out to infinity, as I keep adding more numbers, I get closer and closer and closer and closer to 10. Okay, so I want you to try the next one. I want you to find the first 5 partial sums of the series and then find the sum of the infinite series. So exactly the same thing that we just did, just a different sequence. And then when you're ready to go over it, hit play. Okay, so let's look at this one. This one was a little tricky, and if you didn't notice, you might have to make some changes, but my first term here is plugging in 0. You see that? So my first term is what I get when I plug in 0, because that's the number right in here. So 1/2 to the 0 is 1, and then 1 times 5 is 5. So my first term is 5. And then my R is 1/2 or 0.5, either way. So to find the sum of the first 5 terms, I'm going to take my first term, right? And I have 1 minus, I'm going to say 0.5 to the 5th, all over 1 minus 0.5. And I do my calculator work. Again, I'll show you how I do this. So I usually do 5, 1 minus 0.5 to the 5th. And then I hit enter, and then I divide it by, I know that 1 minus 0.5 is 0.5, but still. I divide it, and I get 9.6875. So the sum of the first 5 terms is 9.6875. 6875. So there are the first 5 partial sums. Then it says find the sum of the series. Okay, so now I want to find the sum of the whole series, which I can do because 1/2 is less than 1. So the sum is going to be equal to my first term over 1 minus my R, which gets me 5 over 0.5, which again is 10, and I promise it's not always 10, okay? I don't know why both those examples, the sum of the infinite series was 10, but so again, as I add new terms every single time, I will get closer and closer and closer to 10. Okay, one more, just finding the sum of the infinite series. I need to know my first term, which is 3, okay? And I need to know my R. Well, I don't know my R, so I'm going to take my second term and I'm going to divide it by my first term. So my second term is 0.3, my first term is 3, and so my R is 0.1. So now I can find the sum is my first term over 1 minus my R, which gets me 3 over 0.9. I don't like that there's a decimal on the bottom, so I'm going to do 3 divided by 0.9. Crazy decimal, not that crazy, but I'm going to change it to a fraction and I get 10/3. So the sum of this infinite series is 10/3. So again, as I keep adding numbers, I get closer and closer and closer to 10/3. Go ahead and try this one, and then when you're ready to go over it, hit play. Okay, so my first term here is 5. And my R, if I take my second term and divide it by my first term, I get, again, that my R is 0.1. I promise it's not always the same, okay? So my sum is going to be equal to my first term divided by 1 minus 0.1. So I get 5 over 0.9. And if I do that little trick on the calculator, I get 50 over 9. So the sum of this sequence, or this series, excuse me, is getting closer and closer and closer to 50 over 9. All right, so hopefully we're feeling good about that. We just have 2 word problems and then we're done. And so these guys are just our application problems on how we can use some of these ideas. So example 9 says a deposit of $50 is made on the first day of every month into a savings account that pays 6% compounded monthly. What is the balance at the end of 2 years? And then this is called an increasing annuity savings plan. And then it uses this compounded interest formula that we've looked at already. One thing that I want to remind you is that if you have a percent, you have to change that to a decimal before you can plug it in for R. Okay, so if we think about this, my first deposit, that's not how you spell deposit, there we go. My first deposit is going to be using the formula here where I put in $50 and I have 1 plus my R is 0.06. My N is how many times a year it's compounded. Well, since this is compounded monthly, my N is going to be 12. And since it's compounded monthly for 2 years, my exponent is going to be 24. And the reason why, this is my very first deposit. So let's say I do this in January, right? How many months is this particular $50 going to be collecting interest, right? It's going to be January, February, March, April, all the way down. And then again, January, February, March, April, right? All the way through 2 years. So this particular $50 is getting compounded 24 times. And if I simplify this equation, I just get 50 times 1.005 to the 24th. So I just simplified the 0.06 divided by 12 plus 1. Okay. My second deposit is going to be the same thing. Now I'm putting in another $50. This is still all the same. But now that $50 only gets to compound interest for 23 months. Right? Because January is already gone. I deposit this in February. Now I only have 23 months till the end of the 2 years. Right? Same thing for like the third deposit. So now it's March, I put in $50. That $50 can only compound interest for 22 months. And so on and so forth. We're not going to write them all out. But the last deposit, right, the one of the 2nd December, put it in on December 1st. And so that deposit only has 1 month to earn interest because you put it in December 1st and then interest is compounded on December 31st. And so this guy right here, this is your A1. So if I actually solve this and enter this into my calculator, it's going to be 50 times 1 point, sorry, I don't know what I'm doing. It's $50 and 25 cents. So that last $50 that I put in only earned 25 cents in interest. So my A1 is $50 and 25 cents. That's my first term. Okay. And then my R is going to be my 1.005. So you don't necessarily have to write all these out. I just wanted to explain why my first term was $50.25, right? That very, very last deposit is only earning 25 cents in interest. My R is 1.005, and I want to find the sum of all 24 months. So I'm going to use my partial sum equation. So it's my first term, which does not have a 1 in it, $50.25 times 1 minus my R, so 1.005, to the 24 all over 1.1.005. 1 1 minus 1.005. And then I enter this into my calculator. I'm going to have to erase it, so hit pause if you need to. I enter this into my calculator, and I get the sum of the first 24 months is $1,277.96. So you've earned almost 78 cents in interest alone. Since it's a word problem, we have to write a sentence, right? So the balance after 2 years is about $1,277.96. And that's what we're looking for. So 1,200 of those dollars are the $50 that you put in, but the $77.96 are what you've earned in interest over 2 years. Okay, so another one, last one for you to try on your own. Only difference is now it's paying 3% and you're putting in $100 a month. Okay, so again, right, your first deposit is going to be 100 times 1 plus 0.03 over 12 times a year. But now I want 4 years, so that it's going to be 48 months that first one gets, which is 100 times 1.0025 to the 48. So then your last is going to just be 100 times 1.0025 to the 1. Okay, so let's figure out what that is. If you haven't already paused it and done it yourself, do it, and then we'll go over it if you haven't done it already. Okay, so we should have gotten that in the last month, you're only going to earn, again, 25 cents. So this is my first term, okay? And then my R is going to be that 1.0025. So to find the sum of the first 48 terms, I'm going to take my first term, which is 100.25, times 1 minus 1.0025 to the 48, all over 1 minus 1.0025. And I do some handy dandy calculator work, and we should get $5,105.85. Okay, so what is the balance at the end of 4 years? So we need a sentence. Balance at the end of 4 years is about $5,105.85. Okay, and that's it. As always, reach out if you have any questions. That's it for 8.3, and see you later.